So now let's get to the actual fun of parallel programming, loops. Why? Because that's where we spend all our time. If you profile your program, 95% of the runtime will be excluding loading, will be in loops. And the good news is we know how to parallelize loop, don't we? If we take a good old loop, C style in this case, a massive loop of 8 iterations, we know how to do that in multi-threaded environment. We just drop our OMP parallel and then we can move on with our life. What's going to happen is, assuming 4 threads, we have thread 0 that will take the first 2 iterations, thread 1 that will take the 2 iterations after that, thread 3, and so on and so on. Actually, that's what we think or we hope is going to happen. That's not what happened. What's happening is this. Remember, once you are in a parallel construct, every single thread does the entirety of what's given to them. So in this case, every thread does the entire loop. There's no coordination between threads to split the iterations between them. So if you try to parallelize your program this way, you will come back to me and say, your workshop was absolute rubbish because I got no speed up yet because all your threads did the entire loop. What we want is another construct that will tell the threads, okay, there's a for loop coming or a do loop in Fortran. The iterations have to be split across the threads available or present in this parallel construct. Why isn't it done by default? Could be a sensible default. Because you may want to do loops entirely. You may be in a scenario where each thread has to do a full loop of step. So we cannot by default distribute all the loops because it might be actually against what you're trying to achieve. So in sequential programming, this is what the loop does, the entire loop. So by default, we keep that semantic in a parallel program. But as always in OpenMP, there's one more directive to learn, and as always in OpenMP, it's just one word. Since it's a for loop, it's called for. In Fortran, since it's a do loop, it's called do, period. So it's hard to make it much easier than this, right? And that does some nice things for you because it goes through all the iterations. It starts to pack them into what we call chunks. I'm going to cover that later. It starts to assign them and so on. We'll see after 2 sections after this what's called schedules, which is where we can start to say how we want these chunks to be moved around, dynamic load balancing. All this just by putting one more word as a clause to this for or do construct. So that's where OpenMP starts to shine, because if you try to do this with POSIX threads, you have to manually calculate the number of iterations you want to allocate to each thread and do some dynamic load balance. OpenMP 2, where it's done. And trust me, I did quite some experiments. It's hard to reach their performance because OpenMP has been around for 25 years, meaning there's been HPC people optimizing everything OpenMP does behind the scenes for 25 years. And remember, the people I'm talking about are the people actually writing the compilers. So when it's Intel people optimizing OpenMP for Intel compilers, it's well done. Same for IBM compilers, same for Cray compilers, same for GCC. When you have NVIDIA taking care of OpenMP for GPUs, for their NVIDIA GPUs, it's well done. So it's as soon as you start to have really OpenMP and MPI in your toolkit, you're good to go to have them with many bits. For C people and C people among them, C people, there's this very annoying thing, which is there's no curly bracket here. If you put a curly bracket, it's not happening. Why? Because it expects the for statement right away. But as soon as you added that little line, now we get exactly what we were expecting. Just one line. And because we had 3 words here and 3 words there, with it was too much effort, so we merged both into a single line, if you want. You can still do them in 2 different lines if you want, or merge them into a single line. So be parallel forwards, and you have fully parallelized the loop. You can't do that with much less effort. And they did a great job. So yes,
a little bit confused about how it like actually speeds it up. So, like, is each thread like running just like a different part of the loop, like I equals 1, I equals 2, I equals 3? But are they doing like sequentially or like all at the same time?
It depends on the hardware you have. If you have a single core, the core will run one thread at a time. So we see, if you have 4 cores, hopefully each core will get a thread. All 4 threads will be run simultaneously. So this is where you will actually start to have 4 iterations done at the same time at any point in time. And this is where, hopefully, the time you spend on that for loop is divided by 4. It's not always as ideal as this, because sometimes you have some synchronization and something, and then it will be 3 times faster instead of 4. But that's where you really start to have the actual performance gains of parallel programming.
It has to be like inside the for loop. It doesn't actually depend on the other loops, right?
Yeah, you have multiple reasons why your speed up, we call speed up the number of times, how many times faster you go. There are a number of factors that can explain why you don't reach the ideal, which is, especially as codes become more complex, extremely hard to reach. We never reach it, basically. But sometimes we even exceed it. We use 4 threads and make the programs more than 4 times faster. Super speed up is called, typically due to cache effects and things like that. Anyway, so now we're good to go and conquer the world, right? We know how to parallelize that. So we just come around to part 4 and we're good to go. I don't say something else here, I just drop it this way. Okay. What comments do you have here? Because I understand why they use this example for the next one. Okay, so we'll leave this one. If it doesn't get your attention for now, it will when we talk about what comes next. For the time being, let's do the loops and have fun. So here what we do is every thread updates the element in the array that is at the index corresponding to its own thread ID. So the first thread updates the first element in the array, second thread updates the second element, and so on. That's equivalent to having a loop of as many iterations as we have threads, where iteration 0 modifies the element 0, putting the value 0 in it. Because the first thread, the ID is 0, the second thread is 1, third thread is 2, and so on. So effectively, this is equivalent to this. Okay?
The first one is done in no particular order. The second one is done in sequential order.
Yes. And what would be this X here? Because I want to do as many iterations as I have threads.
Number.
Repeat. Yes.
Yes.
Now, so if I remove this and if I do that, the program will be correct. But remember the little trick, which is that every thread by default will do the entire loop. So how can we make sure that threads only do a portion of that loop?
Yeah, hashtag P4.
Yeah, it's a for loop, so we use the for. So this will tell the thread, okay, we have that many iterations to go through, split that across the number of threads. In this case, since the number of iterations we have is the number of threads we have, it's a very easy split. 1 iteration per thread, done. Yeah. And that should do it. Yeah, there's nothing coming after. Yes?
Do we need to add the barrier at the end of the parallel for?
We need to add the
Barrier.
Can we get rid of that?
For each
Not anymore, because the for construct by default has an implicit barrier at the end.
Okay.
Which it's not covered here, but which you can remove by using the no wait clause. So the no wait clause allows threads to not wait for all the threads before proceeding with what comes next.
Okay, very interesting. Thank you.
Yes. So this kind of additional clauses you have here and there, they are one way you can get your OpenAP program to a different level by triggering these optimization techniques or creating that room for additional asynchrony to take place. So then, now that we know how to effectively parallelize for loops, we're going to learn something else, which is this example here. I don't know if, yes, this is this example here. Actually, more put it on the other side, which is we have a problem there. We know that when we have multiple threads trying to increment the same variable, we might have this unfortunate timing and end up with a wrong number of increments. However, we know how to fix it. We can put critical. With critical, we're good to go. Problem is, critical means that every thread will get inside this critical region one at a time. But we're trying to parallelize the iterations. So if we parallelize the iterations, only to tell threads you go there one at a time, we kind of negated what we tried to achieve in the first place. So we have another way to do it, which you can do manually again, but OpenAP provides you a very nice way to do it, called a reduction clause. So the reduction clause will take two things. So a clause because it goes at the end of that for construct. Okay. It takes two arguments. Number one is going to be the actual reduction operation you want to achieve, in this case, a sum. And second, the variable in which the reduction is going to take place. Very easy. Now, what it does behind the scenes is the variable in which you will have your reduction. Every thread is going to receive a copy of it that will be very conveniently initialized to the value that is neutral to the operation you want to achieve. So if you do a sum, they're all initialized to 0. If you want to do a product, they will all be initialized to 1, or whatever value was before. This is what I say here. At the end, all these copies will be merged back into the original variable. I have a step-by-step example here coming right next time. Position here. Yeah, true. Typically, we use reductions for for loops, but it's not a clause that is only in the for loop level. You can use it inside a parallel or at the level of the parallel region entirely. So you may have a parallel region, no for loop, but your thread somehow increments some variable. If that's the case, you can still use the reduction at parallel region level, and when you encounter the end of the parallel region, all these additions will be done for you at that point in time. If we look at what happens step by step, so our main thread in blue and our additional thread in red as always. Reduction operator, variable. Yeah, we don't even write sum, we just drop a plus symbol. So it's really because we don't like to type saying this. Anyway, so what happens is every thread has obtains a copy initialized to the value neutral to the operation. So the value neutral to the sum is 0. Because something plus 0 equals the something. Now, let's say that all threads, or each thread, ends up with some value that they want to add back. For example, there's the for loop. They all did a certain number of iterations, and they all end up with a certain number of times they incremented the original variable. So they have their own intermediate totals, if you want. At the end of the for loop, with closing curly bracket, they will all add these copies to the original one. So 148, 23, 163, and then 168, and then 1987. Okay. So it does everything for you. You may say, yeah, that's fun, but that's only for some. And basically, it's like one operator, and we may want to do something more complex. Actually, there are quite a few operators available. And you may say, yeah, but that's only still a very predefined list of something, and I can't. Yeah, well, if you want, you can even create your own reduction operator in OpenMP. Not many people do it, not many people know about it, but you can. It's totally possible to create your own reduction operator. So you have no limit, effectively. So yes, here full transient, which is the same up to that point. Then when it gets to, or the C people start to stick to that, and often people go for the more literal version of it. Coming back to this code, which is incorrect, by the way, for now, because we have these total increments here, which can have a trap, as we know. If we want to use the reduction, we just have to change that part here, the shared total, to the reduction. Why do we have to remove the share with the reduction? We only have to indicate which attribute we're going to use here. No, because it's reduction. Remember, reduction is a bit of a hybrid, because every thread receives a copy, so that an initialized copy, so that sounds like a first private, but not initialized to the original value, initialized to an intermediate value that is neutral to the operations, like weird. And normally, the copies have no impact on the original variable. But this time, at the end, all these values are somehow aggregated back to the original variable. So it's an intermediate between shared and private plus private. That's why you don't have a name for it. You just say it's reduction. OpenMP knows what it means behind the scenes, and you don't have to bother about it anymore. So, just by using one word, again, you parallelized all this and took care of this reduction. I love this. Now, reduction, which is very convenient and typically the bread and butter of OpenMP, because you can have here a super big for loop. If you can phrase this as a reduction, then it's entirely parallelized. You use a big node with 200 cores and you're good to go. Yeah. The problem with reduction is sometimes it's not suitable. What I mean is, try to think of a scenario where you have two different reduction operations done on the same variable. What am I supposed to put here? Min or max? If you put min, it's not correct. If you put max, it's not correct. And you cannot put both. So you just cannot use the reduction here if you use more than one reduction operator. The other case is what happens if we want the result before the end. Because the part to remember is when we have a reduction, the actual gathering, the actual aggregation back to the original variable happens at the very, very end, in the closing curly bracket. So if you need this value before, reduction can help you. So this is why there's another way to do this called atomic. Using the atomic construct, as always in the OpenMP, one word, that's all we need. You drop the atomic here. So that means the instruction that comes after will be done atomically. So let me stop for a second here. This is the first construct we see that relies directly on what the hardware can do for you. So far, it was just software will. Now, atomic is hardware. Because remember how in the example, oh, sorry for that. Remember how in the example with my timing, I was saying, because when you want to increment the variable, you go get the value, you come back, you increment the variable, and you put the updated value back. That actually can be done in one go. As hardware evolved, the instructions possible by the hardware became more and more complex. And one instruction is the atomic version of this. So basically what happens is threads go there, they go to the memory, they see the value, and then directly update it there. They don't go away. So nobody can come and interrupt because it's only one go. So that's how atomic prevents these kind of mistakes. The only trick is, the only limitation is, you're limited by how complex atomic operations can be. Because if Atomic could do everything, we would love this. We're looking forward to it. But sometimes the operation we want to do is just too complex. Oh, we'd like to take it, multiply by 3, divided by 4, take the square root, and put that to the power of 51. Like we can't do everything at once. It's like, we can give you an increment, we can give you a product, we can give you a solid product at the same time. But if you're asking for too much, it's like you need to do something else. So back to reduction or critical or something else. Yes.
I had a question. I wasn't quite clear on what you explained on slide 102.
Okay, that's a very setting it up. Cool.
So yeah, when you do I didn't quite understand how these initialized values are changing internally.
Oh, how I move from 0 to 17 or 0 to something?
Yeah, because I thought that I would have plus 123 over there as part of the reduction operation.
Well, let's say they ended up with different number of iterations, or that the iteration itself contained a different increment. Not every iteration would add +1, but some iteration would add +1 or +5, +10.
Okay.
So at the end, you have different
Okay,
numbers.
so you're doing some local operations, and that's where these variables are changing, and then you're adding 123 to all of them.
Yes, then you bring them back to the original variable. Yes. And that actually reminds me of something else, which took me a while to know, is what they mentioned, which is when we use reduce plus something, I always assume that somehow it meant inside the for loop you had to do plus. So reduce plus my total variable, and I thought inside the loop you had to use my total variable plus equals something. And if I was not using plus equals, it was infringing some semantic, violating some semantics. No, OpenMP doesn't impose that. You may very well have iterations where, let's say, the results are added to the original variable, but you may want a reduction where, I don't know, you may want a reduction where the result obtained here, which was obtained by some values, will no longer be added to the original variable, but maybe multiplied to the original variable. So you can have this I've never found really an example for this, but you might have this 2-layer of reduction. Like I take care of the intra-thread calculations. Inside the thread, I will do sums. And then between threads, I will do products. Why not? We have to, okay, yeah. So with the first one, we need to use reduction, and with the second one, we need to use atomic. So if I want to use well, before I do anything, what's the good practice?
Default none.
Yes. So now that this is done, if I want to use the reduction, what should I do then?
Reduction thread count plus colon thread count.
Yes. Good. And if I want to do the atomic,
Atomic red, like one line.
so like that? Like that?
Yeah.
So that's good. If I compile this program, the compiler will still complain.
If you look at the first one, the reduction implies some thread data scope. The second one still has no data scope.
I.e., this variable here, the compiler will tell me, hey, you didn't tell me if you want this one to be shared, private, first private. So do we want this one to be shared, private, or first private?
Shit, that's right.
Shared, yes. And that, I think, should be it. Yes, we get a great result, which again is not guaranteed by itself. We might have been lucky, but looking at the code, no, we're not lucky. Okay, well then, that takes us to the final section, the final unit for this. 10 minutes, we can do this. So now actually we're going to deal with performance. So far we were only taking care of correctness, how to do something so that it's correct. Now we know how to tackle loops, iterations. We need to think about performance, which is why we mentioned schedule. The schedule clause, which is a clause as well, so you put it at the end of your for or do directive, will indicate how the iterations are going to be distributed to the different threads. You have multiple scheduling times available, all while, which we're going to see. First, I explained that in each slide. So the first one is the static. It's the most natural. Static. So you see the schedule clause, and you say, okay, I want a static. The chunk size I'm going to explain in literally 2 seconds, which is this is going to pack iterations into consecutive iterations into what we call chunks, whose size is determined by the chunk size. Then, once you have these chunks of 3, 5, 16 iterations, you give them to the thread. The function, the first chunk goes to the first thread, second chunk, second thread, and so on. Once you reach the last thread, if you still have chunks remaining, you get back to the first thread and you start again. Round robin fashion. And by default, chunk size is optional. And if you don't give it, by default, it will get to 1/n. So if you have 100 elements, 100 iterations in your loop, and you have 10 threads, by default, the chunk size will be 10. Okay, 1/10 to each of the 10 threads. So if we have a look at actual execution code, 8 iterations in the default I was using before, assuming 4 threads, static, 1 iteration per chunk. We do 1 chunk of 1 thread every time we give it to the first 4 threads. If we have more chunks remaining, which is our case, we put them again in the same order. If we use chunk size of 2, this is what happens. Now, if we use chunk size of 3, you see that the third thread, the fourth thread, actually, the last thread, is deprived from work. It has no work to do. So that's the problem. By having a chunk size that is too big, you may hinder the load balance, because you may end up with threads having nothing left to do, because all the threads before took all the chunks, because the chunks were too big. The advantage of static is that, number one, it's very predictable. Every thread knows at the start, if I'm the first thread and the chunk size is 5, I will have the first element, then the element, 5 slots later, then the iteration, 5 iterations later, and so on. So you instantly know all the iterations you'll have. So that's the first point. And the second point is it has a very low overhead because the calculations are very easy. Your thread 0, you do this, that. Done. There's no monitoring, there's nothing. The problem is when there's a load imbalance. When you have certain iterations that contain more work than others, if you have 10 iterations here and 10 iterations there, it doesn't mean they'll take the same amount of time. Maybe these 10 will take, so you end up having a thread doing a lot more work than the other. You can try to work around by saying, oh, I'll distribute iterations one at a time. But if there are peaks somewhere, then the good thing is I'm very likely to break it down across multiple iterations to multiple threads. Problem now is typically consecutive iterations access consecutive elements in an array. So if you now start having iterations here and iteration over there, it means you're very likely to access in your array an element here and then an element over there. So it means you don't have any cache efficiency here. So that may be turns out talking about cache. Anyway, so that's static. Dynamic is very, very, very similar, but it has one fundamental feature. Same syntax, schedule, dynamic, chunks, so far so good. It distributes the first n chunks to the nth thread, like static does. The difference comes with what comes next. With static, all the chunks are distributed, or the remaining chunks are distributed the same way to the threads. With dynamic, now it's the first come, first served. So every thread is given one chunk. And then it comes down to threads coming and asking for more work. So once I gave my first chunk to every thread, I'll wait for a thread to come back and tell me I want one more chunk, and then I'll give one more chunk. And that's very nice, because then we can have some load balance that I'm going to mention in a second. The sneaky difference is chunk size is optional again, but by default, the value is not your 1n, it's 1, 1, I don't know. Not my decision. So if we look at this example, the same example, same array, same number of iterations, same number of threads. The first chunk is given to every thread. Now, the 4 chunks remaining will be given to the thread that comes and asks for more work. So let's say it's thread 1 that finished first, it gets the next. Thread 3 is available next, okay, it will get the next. Then if it's thread 0, if it's thread 0 again, it will get again. It's really whoever is available first. That allows you to deal with situations where, for example, iteration 2 was super big. This one was super big. So it means that this thread is always busy. So no need to give it more chunks. And dynamic will not, because thread 2 will never come back asking for more. So it automatically balances your program. You can still change the chunk size, make it 2, for example, and then all the iterations are distributed directly in the first round. So you can address this load balance, but you have a bit bigger overhead because there's this monitoring happening, and finding the right chunk size is not always trivial. Anyway, so now the last 3 are more interesting. We don't use them much. Guided is one where the chunk size starts to be 1/10 of the remaining number of iterations, and it will always be that. The second chunk will be 1/10 of the remaining number of iterations. So if I do again the example of 100 iterations and 10 threads, first chunk size 10 iterations, second, a 10th of the 90 remaining, then a 10th of the 81 remaining, and so on and so on. And the chunk size is for the minimum remaining. That's something else. It's getting late, so I'll play with this. I'll just mention auto, which is the other one. Oh, that's fine for now. It's fine. Mention the auto. Auto is my favorite because just tell OpenMP, okay, I trust you, do something. So it's no longer static, dynamic. It's like you tell OpenMP runtime, I trust you, do whatever you want. There's a very powerful yet overestimated feature of this is you allow the OpenMP runtime to use techniques that are not static or dynamic or something. So it may use a very implementer-specific technique to use load balancing, built-in support from whatever hardware they have. Something. But yeah, you don't really control anything. You just big leap of faith. Like, okay, I'll trust you. And the runtime, which is way too complex for that. Let's do it together right away. So we get a bit faster. You have all the exercises anyway, so you can do them on your own time. You can try them again. There's really no problem. So the first loop, every iteration consists in waiting for the same amount of time. So every iteration has the same work to do. So what would be the nice schedule to apply here? Since they all have the same amount of work. Static. Exactly. So if we try first to run it, I need to get to the 8. Okay, so the first one takes 1 second. Okay. The second one takes 550, and the third one takes 530. Okay. So now let's put that in. Let's compile and run. Okay, the first one got 10 times faster. That's okay. Not bad, not very. I think at some point the iterations are so light but there's nothing else to be done at the end. Still 0.1, that's surprising. I'm the only one using it. Okay. I would have expected it much better here. Okay, so the second one, the second one is tricky. So the second one, the amount of work per iteration, what does it do? Does it go up or does it go down? Because for the first iteration, we have max. For the second iteration, we have max minus 1.
Yeah.
So it means that the amount of work goes down.
Yeah.
So which one should we use? Online, feel free to participate as well if you have an idea. When we hear sorry?
I think your dynamic would be a better choice.
Yes. The trap is to go with guided, because guided, remember, has this ability to make the chunk size smaller and smaller and smaller. So if we try to use guided here, it will be actually counterproductive. Why? Because the iterations at the start have the biggest amount of work and they go down. So it means that the first chunks, the biggest one, will contain all the heaviest iterations. So I designed it to be counter-guided. However, we can make it super guide friendly anyway. You just have to reverse the order.
Minus 1 and equals.
And equals here. So here we start by the end, from the end. So we start from the iterations are super light. So then we can have a big chunk and a slightly smaller chunk for iterations are slightly bigger and a slightly smaller chunk for even bigger. So that's a nice way to deal with it. Let's see what happens. I didn't update it. 0.1, 1 second. Okay, so we made it 5 times faster. Okay, I'm still disappointed. I was expecting to see something faster. I'm still the only thing. I guess.
How many threads are you running with? 32?
Yeah. So it's
I mean, it's a lot of threads. There's a bit more overhead. You could try to set the threads something lower and just check it.
Yeah, I was expecting that should have been a clear times. It actually always was a clear times 32. Perfect speed up. There's something happening somewhere here. Oh no, of course there's nothing happening here. 0.1. We wait a 1/10 of a second. So even if all threads doing it at the same time, it takes 1/10 of a second anyway. So that's why it takes 1/10 of a second, because they all do it at the same time. They take 1/10 of a second. That's why. So that shows actually that using more threads is not always helpful if there's nothing else to parallelize. Anyway, and the last one is basically random, because I put some random in there. So you cannot determine in advance how much time you're going to spend. So here, when we parallel for, you can either go auto. Let's see what it gives. So 0.1 here, 1 here, 0.9 instead of 5.3. So, okay, 6 times faster. Okay, cool. And if I do dynamic instead? Oh, to the same performance. Good. Okay. That's
So do you set the random seed or is it always the same random?
It's always the same. So we can have comparable results. Okay, so yeah, here you see just by putting one word. Again, this is because you cannot get any more than 10 times faster, and I strongly think this is the same because the biggest iteration is 1 second. That's why you cannot go any lower than this. Because usually we don't have 32 threads available. We go to 204, so I designed it for 204. Maybe I should design it now for 32. Anyway, so yeah, this is the end of that part where we've seen the different ways to deal with that. There is a lot more to see. When I mean a lot more, I mean a lot more. Task-based parallelism, part of loop styling, and cycle threading, and so there's a lot more to see. You can visit the MP4 website to learn everything.